Swastiastu. Greeting everyone. Today I'm bringing you a presentation about metallurgy, specifically modern alloy and production. My name is Putu Januartha Prayoga Putra with name 2305 1070. Okay, be next. I'm gonna find this first. Next. Main reference I uses is Metallurgi for the non-metallurgists, the second edition. Next, the context I use is chapter 5. It's the first is effective of alloying on solidification. Second, solidification structures. 3 melting furnace. 4 molten melts processing. 5 primary production casting. 6 foundry casting. 7 non-ferrous casting alloys. 8 foundry metallurgy. First is material the presentation we decided now is 5.1 effective of alloying on solidification. The solidification of alloying is a complex process and it is most easily understood by examining how the solidification characteristic of alloy differ from those of pure metals. This is a topic discussed to some extent in the chapter 2 and is barely expanded in this session. First is solidification of pure metals. When a pure metal begins to melt, the solid liquid mixture stays at the melting point temperature until all of the solid has completely melted. Second, solidification of alloys. The solidification of alloys is more complex than that of pure metals because the different elements in alloy possess different melting temperature. Then the next for the presentation. Pure metals give up their latent heat of fusion and solidify at a single temperature. If a pure metal is melting an alloy to solidify in the melting crucible, a thermocouple placed in the metal during solidification called trace a cooling curve like that shown in figure 1.5. Just like this picture is the first pure metal non-fragrance metal present and second pure metal fragrance metal present. A characteristic cooling in the picture, characteristic cooling curve A for pure metal with no Frangian metal present, and B for pure metal with Frangian metal present. The presence of impurities reduces the amount of supercooling because impurities produce a strong nucleation effect, but the melting point itself remains unaffected. See typical cooling curve for a solid solution alloys. Note that freezing L to H occurs over a range temperature. Open the next. Aluminium silicons alloy are the other example of a major family of examined casting alloys with autistic point. The aluminium silicon autistic is located at approximately 12.6 Bt% Si and 577 Celsius on the binary phase diagram figure 5.2. It's like this. Figure 5.2 aluminium silicon phase diagram with S-chas microstructures of alloy with various composition above, below, or near the eutectic compression of 12.6% Si allows with less than 12.6% Si are referring to as hypertectic. those with close to 12.6% Si as autistic, and those with over 12.6% Si as hypereutektic. The next for the method, allow the processor relatively wide pressing range can be thrown out to void formation, except porosity during casting, while alloy composition near aesthetic melting point there at freezing range is much narrower, can have clearly advanced in casting specific shape or geometries under certain conditions. This is a particularly important consideration in aluminum silicon alloys, which have been used to design in the automotive industry for casting engine blocks, like a figure 5.3. This is the casting of engine blocks, and the casting is pattern loss from casting of an automotive engine block, just like this, the casting. And with the next chapter is 5.2 solidification structures. The solid liquid interface during solidification normally exhibits one of the three types of crystal growth in the liquid: planar, cellular, and dendriticity growth, as shown in picture 5.4. 5.4, this is another 5.4 picture. The type of growth is controlled by the manner in which heat is removed from the system. When the liquid ahead of the solid liquid interface X0 has a positive temperature gradient, heat is removed from the liquid by condition through the growing solid. Because the temperature gradient is linear and uniformly perpendicular to the interface, a smooth interface is maintained and growth in the planar into the liquid picture 5.4a. This is picture 5.4a. As you can see, planarly growth in the side front temperature. The side is we have a solid and liquid, and the front is the blank, and temperature is in the front solid to liquid. It just out to the liquid. And with the next to the next. Okay. When there is a temperature impression and the temperature descends ahead of a the solid liquid interface, then either cellular or dendritic growth will occur. A factor 5.4 B and C. The difference between the two is matter of agree. Small undercoolings tend to produce cellular growth, while large undercoolings tend to produce dendritic growth. In the pure metal, undercooling can result from thermal supercooling, while in alloys, it can result from the combination of thermal and constitution supercooling. It's like that in the picture. It's B and C. So B is cell growth, so it's like that. There's difference between the dendritic growth. Look at, as you can see, this is a different. Picture 5.3 affected and undercooling of solidification structure. We're gonna next. The thermal supercooling cellular growth as illustrated in figure 5.5. This is a figure 5.5. Occurs when the advanced planar solid liquid interface becomes unstable and a small spike appears on the interface that then grow into a cellular type structure. The planary surface becomes unstable because any part of the interface that grow in the head of the main enter region in the liquid, then it is at a lower temperature. This is a Victor 5.5 transition from the planetary to center grow. As you can see, the heat is going forward, and the different and the change is going over there. Then the next, at still higher undercooling and higher growth velocities, the cell grow into rapidly advancing projection. Sometimes it's complex geometry. Dendrites are small crystal neatly shaped like pine trees. In the picture 5.6, just like this, and the shape like a pine tree. So named after Greek word dendros to tree. Picture 5.6, scaling electron micrograph of dendrites in the shrinkage region of a steel casting. Original magnification 42x, source reference 5.1. And the next. First is constitutional supercooling. While dendrites can form a limited even in the pure metals due to temperature inverse, they are more preferred in alloy because of the additional undercooling due to constitutional supercooling. Constitutional supercooling areas because of the segregation of the alloying metal element ahead of the solid liquid front. As an alloy solidifies, the chemical composition of the remaining liquid and the non-reformed solid continue to change. Second, a solidification zone. A metal cast into a mold can have up to 2 or 3 distinct zones or the type of grain growth. A chill zone, a zone containing clumping grains, and a center acquisition grain zone. Like you can see in the picture 5.7. The picture 5.7 is an ingot intrusted A thread of the steel ingot showing a chill zone, a crucium zone, and a acquisition zone. B 1,100 aluminum ingot without excess acquisition zone in the center. C cast 100 aluminum quasset against top and with grain refined at the bottom. Then the next chill zone nucleation first occurs on the interior surface of the mold because of the mold is cooler than a metal. As a result of the temperature difference, the nucleation rate is initially high and the average grain size is typically small. Its nucleation even produce an individual crystal or gain that grow dendritically in a direction roughly perpendicular to the mold wall until impacts on the ethyl grains, like a picture 5.8. This is A, B, C, D. Picture 5.6 progressive grow of the dendrite into grains. This is our change. The first, second, third, and fourth. The next after this, the center acquisition zone, a third region at the center of same allows casting functions of smaller grains that are randomly oriented and nearly acquiescent, meaning crystals are similar and lightweight and welded. As freezing process, the thermal grain decrease and this is cause dangerous to become very long. Breakdown and columnar growth may occur as a result of fracturing of the very long dendrite grain by conversion correct in the melt. There's broken arm in the figure 5.9. It's a figure 5.9 columnar equation. Picture 5.9 schematic illustration of columnar and equation ingot structure. Source Ref 5.2 Council of the Marathon Fleming. Go to next. In alloy with a wide freezing range, the information of the first solid phase crystal cause some alloy enrichment in the liquid region of the newly formed crystal. This is a local enrichment suppressed growth of the first crystal but created condition favorable for the nucleation of the second set of crystals just beyond the first set. Picture 5.10 A and B. This is A and B 5.10. Picture 5.10 solidification in an alloy with a wide freezing range. A and B are the state. Gonna next. The process is repeated as many times as necessary. Figure 5.10 C and D. The grain truths tend to be equation if crystal grow in the sufficient suppress. The identical grow also can be suspension. This is a picture of 5.10 solidification and alloy with a wide freezing range. C then D and D letter state. This is a C and D. We're gonna next. Non-dendritic solidification for the semi-solid processing. Although nearly all the commercial alloys dendriticals with either a columnar or an expressed dendritic structure. An important excepting in the non-dendritic solidification for the solid processing. Solid processing alloys are products with a unique non-dendritic microstructure in the figure 5.11 with important effects from book shaping. This is a picture 5.11 microstructure of a thick cast similar process AZ91 magnesium alloy. A. Conventional etching. B. Electronic etching. And polished light elimination. Color help discussion grain oriented and the ratio of the maximum to maximum grain diameter contains a scabbard cut. Gonna next something. During the early stage of the solidification, the microstructure of the off-cast alloys can be altered from a derivative structure toward a rosetted of spherical morphology. Figure 5.12. This is figure 5.12. Force convection. Growth of the mechanical engagement increases and turbulence in the liquid switch from the solidification of the global semi-solid structure. Picture 5.12 schematic illustration morphological transition under force convection to develop semi-solid structure result. Search Ref 513. Next. 5.3 Melting furnace. A wide variety of furnace technology are available for melting metals. In the steel making, for example, pig iron is produced in a blast furnace from iron ore, limestone, and coke. Picture 5.13. It's like this. 5.13 the picture. Because it contains an excessively high level of silicon, manganese, carbon, and other elements into molds. This is a picture 5.13. Follow diagram of melting process and used to produce steel. Next. The type of treatment using all steel include a variety of the common metal, including stirring or heating process for deoxidation, decarburization, and adjustment of the chemical composition, as well as degradation. Some examples are shown in the picture 5.14. Following little treatments, sometimes acidification, demelting, or refining steps are performing prior to casting. This is a picture 5.14. Example of the leading treatment using to refine molten steel. A. Bottom stirring. B. Powder injection. C. Vacuum oxygen decarburization process. D. Vacuum degradation. So the next. Electrical arc furnace. One of the furnaces most commonly used to melt steel alloy in the electrical arc furnace in EAF. A typical EAF is a refractory lignite vessel with a bowl-shaped heart that is covered with a retractable hemispherical roof. The roof usually may be refractory line, or in the case of large furnace, it may be the water cooled. The roof has been several openings through which one of more graphite electrodes can be lowered into or withdrawn from the furnace. This is the picture of 5.15. Schematic diagram of the electrical arc furnace. We're gonna next after this. Induction melting is performed by applying an alternating current through an education coil, which produces a magnetic field that generates a current flow in the charged material through material condition. This is generated heat and melt the changed material. Then amount the energy absorbed by the charge depends on the magnetic field intensity. Electrical intensity of the charge and the operating frequency. When the charge is liquefied, the line of the magnetic flux also causes metal movement, which induces electromagnetic scattering, like picture 5.16. This is picture 5.16. Across a sectional few of the coreless type induction furnace in illustrating for quadrat string action, which aids in products and homogeneous melt. The next, at their most basic level of from and vacation model, crable furnace are similar in the concept to their early prototype. Modern material of the construction, Victor 5.17, have improved their thermal efficiency and surface life considerably. Crushed cribbles may be as small as teacups or may hold several tons of metal. They may be fixed in the place within a furnace structure or may be desired to be removed from the furnace for pouring at the end each melt. This is a picture 5.70. Electrical bailout crockrable furnace cross tendency of Morgan Crockable. The next 5.4 molten melting procession. Yeah. Molten melts are processed and handled in the various ways, depending on the alloy and melting procession that are used. Sorry about that. So we're gonna continue. Melting is a basically way of combination element for the purpose is alloying, and the overall chemical compression of the molten alloy must be carefully controlled and processed before casting can take place. The reactivity of the molten metal at high temperature also requires specific processing technique for the removing or the preventing the formation of inclusion impurities or dissolved gas in the melt. Dross is normally considered to be an undesirable metal, which is supported by the definition found in the most dictionaries come on molten metal. Dross is undesirable because it represents a loss of someone's molten metal for casting. Next, fluxing of molten metal is often the first step in the updressing of clean metal. Fluxing is a term commonly used in the foundries and mantling department that refers to molten metal treatment from the addition of reactive chemical compound or incurred gases. The various infections of molten metal friction additive either singly or in combination include removing inclusion, impurities, or dissolved gases from the melt, preventing extraction for formation of the solid phase inclusion, preventing and or removing oxidized product on the furnace wall, injection or distributing alloy constitution. Thus, fluxes are commonly used to some extent with virtually all molten material operation in both of foundry and in the production of milk product. Fluxing can occur throughout the various state of metalling and handling of molten metal from the melting of holding furnace to the transfer ladder. Next, 5.5 Primary production casting. The primary production of metal normally involves either ingot casting or continuous casting of the production such as strip, sheet, wire, or bar. Continuous casting offers central benefit for static casting, but not all metal can be continuously cast. Raw products are typical cast in the ingot from the for subsequential hot working in reduction operation. Foundries also require the use of ingots. Factor 5.90. It's like this, Factor 5.90. That can be remelted, sometimes called pig ingots, to provide specification compression. This is Factor 5.90. Automatically stacker of ingot for foundry melting. Contrast of lighter metal age. Sorry about that. We're gonna next. Sorry again. Gonna next. Sorry about that. Okay. Continuous casting can be either vertical or horizontal. Horizontal casting is limited to metal with lower melting points, such as copper, aluminum, and cast iron. In vertical continuous casting, Factor 5.20. This is Factor 5.20, just like this. Molten metal is proper into the caster from the top. The temperature of the metal is reduced as it presses through the water-cooled mold. Solidification starts from the middle of the mold, beginning at the outer surface of the mold and moving toward the middle of the embryonic ingot. From this point, the liquid solid metal assumes a wet shape as it passes through the solidification zone and through the first part of the water spray zone. As the metal is solidified from this point forward. Next. For rock aluminum alloys, the dry steel or DC semi-continuous casting process, or one of its variation is the preferred method in use today is production ingot and billet product. This process developed in 1933 by Whitty and al. Involves pouring aluminum into a shallow water-cooled mold of the cross-sectional shape of the ingot or sensation desired, like a Factor 5.21, just like this. When the metal begins to freeze in the mold, the fast bottom in the dirt mold is lower at the control rate, and water is sprayed on the surface of the freshly solidified metal as it comes out of the mold. Almost all conventional aluminum ingot production from fabrication are cast using this process. Gonna next. The DC casting progress can produce fine-grained ingot with aluminum upward segregation at different high production rate. The high production rate. The process can be vertical or horizontal, like a Victor 5.22. Compared to traditional ingot casting method, the DC casting process makes it possible to cast the same alloy with a minimum amount of ingot surgery because the liquid metal fishing from the form is almost horizontal and the material pressure from the bottom to the top of the ingot. Putu 5.22 directed chill aluminum casting A. Rolling ingot with a molding in the background. B. Bulleted in the 4 stand horizontal directed chill caster. G. 20 stand horizontal directed chill center of the foundry ingot. Image B and C are constantly of the light metal age. Prep 1995. The next, and take a break. Wait, sorry about that. We're gonna continue. And material 5.6 foundry casting. Foundries use foundation method to cast parts with complex shape and interior surface. Molds are made in the variety of ways so that the molten metal fed into the mold cavity result in the part with the shape and dimension of the finished form. Sorry about that. I'm gonna next it. Continue. The choice of the molding method depends on the several factors such as part size and shape, quality, tooling, and the molten melt began brought into the mold. Shape casting method can be divided into 3 broad categories. First, casting with expandable mold such as sand, plaster, ceramic, and graphite molding. Second, casting with reusable permanent molds. And third, casting with reusable permanent mold. Mold with high pressure metal injection of the metal into the mold, such like die casting, pressing casting, and semi-solid processing. Then next, casting with expandable mold provided tremendous freedom of design in the term of size, shape, and production quality. Expandable mold methods are classified further as either. First is expandable mold with a permanent preparation. Second, expandable mold with expandable preparation. When permanent preparations are used, the mold must be separable into 2 or more parts in order to permit withdrawal of the permanent pattern. The permanent pattern is the negative or minor image of the part can be cast, and the patterns are used to form the cavity from the cup top and drop bottom section of the mold, like a picture 5.23. After the parrots are removed, the cup and rock sections are sealed together for casting. The next, this is like picture 53, a major component in sand molding. A preparant assemble for crop and rock, it's like this, assemble it. B, a crosser section of molding with course, like this. We're gonna next it. Unlike permanent prepared for molds, expandable prepared are positively replace replica of the part Picture 5.24. It's like this. In the loss from casting for the sample and from a preparant is placed in the fast sand bag. Sand is then added and compacted around the foam pattern. During pruning of the molten metals, the foam evaporates are the metal solidifies in the result cavity. This is picture 5.24 cast manifold with positive pattern for loss from casting. The next step. In the investment casting, a chemical slurry is applied around a disposable pattern, usually matched and allowed to harden to form a disposable casting mold. The pattern is disposable because it's destroyed after the ceramic mold hardens. After casting of completed, the ceramic mold is removed to recover the part. There are two different processes for making investment casting mold: the solid investment solid mold processing and the ceramic cell process. The ceramic cell process, picture 5.25a, has become the predominant technique for engineering application. Displays the solid investment process, picture 525b. The picture 525. Schematic of the investment cast part: A. Salmon investment casting, B. Salmon investment casting. Like this. Next. In many applications, the higher mechanical property can justify the cost of a permanent mold when product volume does not. Their metal molds are usually made of iron or steel and have a product life of 10,000 to 120,000 casting. Metal that can be cast in permanent molds include the aluminum, magnesium, zinc, and copper, allow the hypertectic gray iron. The vast majority of permanent mold casting are made of aluminum alloys, like a picture 5.26. Picture 5.26. A sample of aluminum permanent casting: control arm, brake master cylinder, and caliper, steering knuckle, valve housing, and engine mounting bracket. Sorry about that. I'm gonna continue. Correctly of the General Aluminum Manufacturing CO. Next, part products by the die cast process are showing in the picture 5.27. This is 5.27. This is a part usually die casting process. Squeeze casting is the term commonly used to refer to a die casting process in which a liquid alloy is cast without turbulence and gas entrapment, and subsequently held at high pressure drop out. The freezing cycle to yield high quality heat treatable component. The next, the 5.7 non-ferrous casting alloy. In this case, in the term of tonnage, cast iron is the most commonly found alloys constituting approximately 3/4 of the worldwide products of casting. For example, the 40 costly of the world casting products towards the total worldwide production of the casting in 2005 at 85,741,068 metric ton. Tonnage of the cast alloy in the year was distributed among the various alloy systems as follows. This is the graphic. Iron, iron, steel, copper, aluminum, magazine, zinc, other. It is like a total of all of these. The next of this. Aluminum casting alloys. Aluminum casting alloys are the most versatile of all common foundry alloys and accordingly have the highest castability ratings. As casting material, aluminum alloys have those favorable characteristics: good refillability for filling thin section, low liquid use temperature relative to those requirements for many other materials, rapid heat transfer from the molten aluminum to mold, proven shorter casting cycles. Hydrogen is the only gas with appreciable solubility in aluminum and its alloys, and hydrogen's solubility in aluminum can be readily controlled by processing methods. Many aluminum alloys are relatively free from hot shot, cracking, and tearing tension. Chemical stable, good as cast surface finish with lustration surface that suffer few or not blemishes. And next, this is the next 518 powder metallurgy. One of the more recurrent metallurgical development in the manufacture of metal alloy is the development of powder metallurgy (PM) processing. Metal powder can be produced using a wide variety of the mechanical metal as well as by chemical and electrochemical method. Gonna next. Sorry about that. Gonna continue. Atomization is the dominant method for the production metal and fairly light powders from the aluminum, brass, iron, low alloy steel, stainless steel, tool steel, super alloy, titanium alloy, and many other important industrial alloys. Water atomization in the term of tonnage, water atomization is now is preeminent mode of the automation for metals, especially ferrous metal powders. The large commercial application of the water atomization is the iron powder for press and sister application, and approximately 60 to 70% of the world production of iron powder, which now total more than 100,000 metric ton per year, is produced by water atomization. Next. The general type of atomization process encompasses a number of industrial and reacts metal include two fluid atomization where the liquid metal is broken up into development by impregnement of high pressure jet of the gas, water, or oil in the factor 28 A and B. This is factor 28 A and B. It's like this. Next, second, centrifugal atomization, where a liquid stream is dispersed into droplets by the centrifugal force of the rotation disk. This cup or electrode in the factor 28C, just like this. Third, vacuum or solute gas atomization, where a molten metal is supersaturated with a gas that causes atomization of the metal in the vacuum, like a factor 28D, like this. And the fourth, ultrasonic atomization, where a liquid metal film is agitated by ultrasonic vibration, like a factor 28A, like this. And the next, water in atomization generally products irregular powders are of relatively high oxygen content. So I'm sorry about that again. Today is not having great feeling, and we're gonna continue. A schematic flow sheet of the water atomization process is shown in the figure 5.29. This is figure 5.29. The major of component is typically installed into the metal facility and atomizing chamber. This is water pumping or recycling system and powder dewatering and drying equipment, melting metal following standard procedure described profusely in this chapter. Induction melting, arc melting, and crucible melting are all suitable for production procedure. To the next, gas atomization differently from water atomization is severely respect rather than being dominated by the pressure of the medium in water atomization. It is found that the gas to metal ratio is the dominant factor in the contouring powder particle size, with medium particle size being related in closer to the square root of the gas-to metal ratio. Gas atomization units also come in a much wide range of design than water atomization and are classified as either conformated or free-fall modular configuration, like in figure 5.30. This is figure 5.30 for two fluid atomization with A free-fall design, gas or water, and B continuous noisy design, gas only. Design characteristic A angle from the free-fall metal and atomization medium. A distance between metal and nozzle. D diameter of condenser metal nozzle. P precision light of the metal nozzle. Source of rate 5.6. Go to next. And that's all the presentation I'm gonna give today. I'm sorry if this presentation really really so much bad action over my uh, English speaking. And this is my first time to presentation with English. So I hope this is the first video I using English accent and maybe English language. Maybe I'm gonna be better in next video. So I hope you enjoy and thank you so much for watching. And I'm sorry if I so much feel like uh, get far away from the camera because sometimes I just don't feel so much good today. And thank you so much. And I'm very sorry for maybe not all I'm saying is clearly everybody can understand that. And I'm I'm sorry, and I'm gonna be better next time. And thank you, and have a nice day. And maybe we're gonna uh, meet again in the next video. And see you in the next video. Goodbye. Thank you so much.